Since the mid-20th century, two theories of physics have offered powerful yet incompatible models of the physical universe. General relativity brings space and time together into the then portmanteau spacetime, the curvature of which is gravity. It works really well on large scales, such as interplanetary or interstellar space. But zoom into the subatomic, and things get weird. The mere act of observing interactions changes the behavior of what is presumably totally independent of observation. In those situations, we need quantum theory to help us make sense of it all. Though scientists have made some remarkable attempts to bring these estranged theories together, viz., string theory, the math behind the theories remains incompatible. However, new research from Antoine Tilloy of the Max Planck Institute of Quantum Optics in Garching, Germany, suggests that gravity might be an attribute of random fluctuations on the quantum level, which would supplant gravity as the more fundamental theory and put us on the path to a unified theory of the physical universe. In quantum theory, a particle's state is described by its wave function. This function allows theorists to predict the probability that a particle will be in this or that place. However, before the act of verification is made via measurement, no one knows for sure where the particle will be, or if it even exists. In scientific terms, the act of observation collapses the wave function. Here's the thing about quantum mechanics: it doesn't define what a measurement is, who or what is an observer, a conscious human. Bracketing all explanations to observed phenomena, we're stuck with paradoxes like Schrödinger's cat, which invites us to consider the equal possibilities that a previously boxed cat is, as far as we know, simultaneously dead and alive in the box, and will remain as such until we lift the lid. One attempt to solve the paradox is the Girardi-Rimini-Weber GRW model from the late 80s. It incorporates random flashes that can cause the wave functions in quantum systems to spontaneously collapse. This purports to leave the outcome unbesmirched by meddling human observation. Tilloy meddled with this model to extend quantum theory to encompass gravity. When a flash collapses a wave function, and the particle reaches its final position, a gravitational field pops into existence at that precise moment in spacetime. On a large enough scale, quantum systems have many particles going through innumerable flashes. According to Tilloy's theory, this creates a fluctuating gravitational field, and the gravitational field produced by the average of these fluctuations is compatible with Newton's theory of gravity. If gravity comes from quantum processes but nevertheless behaves in a classical and Newtonian way, what we have is a semi-classical theory. However, Klaus Hornberger of the University of Duisburg-Essen in Germany cautions the scientific world that other problems must be tackled before Tilloy's semi-classical solution can warrant serious consideration as a unifying theory of fundamental forces underlying all modern physical laws. It fits Newton's theory of gravity, but Tilloy's yet to work out the math to show that the quantum theory also describes gravity under Einstein's theory of general relativity. With the greatest explanatory power, physics is one of the most exciting scientific disciplines. But the key to unified theories in physics is patience. As with Schrödinger's cat, the will to know alone cannot fill in the gaps of what we simply don't yet know. This article was originally published by Futurism. Read the original article.